So, okay, so I'm an applied mathematician, so I'm going to talk about the stochastic optimization, which is a tool that appears in many models in image processing, right? So basically, the problem is how to estimate the parameters of in our model. So let me just set up the problem. So, okay, so we're going to assume that there is a parameter that we're trying to estimate, the parameter alpha. Where am I? Here. Right, so we have a function, f of alpha, which we can think of like our loss function that depends on the parameter theta. And the only issue is that it's not easy to evaluate the loss, right? The loss is given as the expected value of some random variable, right? In the image processing examples, it's just the sum of the errors, right? So it's a big sum. You can think of it as an expected value. So what is the difficulty? Well, this function has some noise. Every time we get a new sample or we get a new image to train our model, there is some noise that we are adding to the model. So if we want to evaluate the function, let's say by Monte Carlo, then well, we have a statistical error of the size of 1 over the square root of L, where L is the number of samples. So, so how do we optimize this type of functions? Well, the standard tool is the sensitivity analysis for the model, right? So if you're familiar with neural networks, you can just think of theta as the weights of your neural net, and then the sensitivity analysis is just to calculate the gradient, or in other words, how your loss function is changing with respect to the parameter theta, right? So the sensitivity analysis is just calculate the gradient. So what do we want from this gradient? Well, for most applications, we want that it has a low bias, right? So the expected value of our gradient estimate is the actual gradient. And it shouldn't be harder to evaluate the gradient than it was to evaluate our function. We also want the standard deviation to stay about the same. Again, in process imaging, in the processes of images, we don't have to worry about this. It's done. So we'll talk about this later. But it's just the general setup. But it's not easy, you know. In the actual rule is if you have a very complex model, it's going to be hard to do the sensitivity analysis. So neural networks and this type of models that are not as complicated, so we can do it. Anyway, so so what do we do once we have an estimate of the gradient, right? Well, the plain optimization is just the Robbins-Monro type of optimization, which is the following. We have our previous estimates of the parameters, our new estimate is just the previous estimate minus one constant, that 1 power of n, when n is the number of steps that we have so far, and a matrix Kn multiplied by the gradient estimate, right? So the usual method is just to take the simplest K, which is a multiple K of the identity matrix, and take the power of gamma to be 1, right? That's the usual stochastic gradient descent. Now, it is very well known that the optimal Kn to pick is H inverse, where H is just the Hessian of the function that we're trying to optimize. At the optimal, here this alpha should be theta, at the optimal parameter. And it's also well known that there is a big difference when H is ill-conditioned, right? But, I mean, obviously, if we are estimating the gradient, it looks like a little ludicrous to try to also estimate the inverse of the Hessian, right? But what we're going to see is that this can be actually done. But before that, let's explain why we really want to do that. I mean, what's wrong with the gradient when we just take K times the identity as our matrix Kn? Well, it's very standard to show that if we have if we have that this matrix, 1/2 of the identity minus this constant K, that is just the step size, let's say, multiplied by H, if this has negative, well, if the eigenvalues have negative real part, and theta n converges to theta star with probability 1, then we have the following result. If you evaluate your function, your loss, right, in your current estimate, and you subtract your loss in the optimal estimate, and you multiply it by n, that has a limit in probability. So in distribution, this converges to something that is not normal, right? Because you see the left-hand side is always positive, right? So it converges to well, here Z is a standard normal, so we have like C times C transpose. So it's just like the norm of a normal random variable is positive. But we can calculate here the sigma that appears on the right-hand side and the H. These are, again, this is a standard. The sigma is just kind of like the square root of R, where R satisfies the Riccati equation. So here is the Riccati equation. What do we have in the equation? We have K, the matrix that we are using to do the update, like the Kn. So here this K is just the small k times the identity, but I just left the big K for this equation. So anyway, so we have K, we have H, which is the Hessian of our function, the identity, the R, which is the solution well, the solution of the Riccati equation, and we have here this sigma, right? So what is this matrix sigma? This is just the covariance matrix of our gradient estimator. So anyway, the matrix sigma is just the covariance matrix of our gradient estimator at the optimal parameter theta, right? So anyway, it looks nice, but I mean, how bad is this, right? So how bad is this error that we're getting, right? So we can calculate the expected value of this random variable and the result, which is what I calculated because this wasn't done before, is a sum of two terms. And here is the very interesting part. The second term vanishes when we have that our step, well, here again I have the small k, but if we had the big K and K was H inverse, this second term will just completely vanish. It wouldn't be there. So all our error will be just the first term, right? But since we are not using the inverse of H, we're just using a constant times the identity, this is the error that we get, right? And again, you see it and you are like, okay, so what, right? Well, this is what happens. So we can estimate a lower bound for that second term, and we get the following. We get, well, first of all, we do the spectral decomposition of the matrix H and the matrix sigma, right? And we put just the lambda, the diagonal matrix with the eigenvalues of H, just in increasing order. The same with sigma. And, well, this is the bound, a lower bound for the error of the stochastic gradient. So D1 is just the first eigenvalue of the covariance matrix of the gradient. Then we have the trace of H inverse. And then here we have, again, D1 and lambda 1 and lambda p, which are the eigenvalues of lambda. These are the eigenvalues of H in the matrix lambda here. So the smallest one and the biggest one. And here we have the Frobenius norm of the difference between H and diagonal matrix, just lambda 1 times the identity. So what happens when H, the Hessian of our function, is actually a full matrix? Well, the first term that is always there is of the size of P, the number of parameters that we have, right? The trace of a matrix is just the sum of the eigenvalues, right? So this is order P. But the second term that has the Frobenius norm right here, this is order P squared, because if we subtract the diagonal, the terms that are outside the diagonal are P squared. So the error that we have with the stochastic gradient when H is a full matrix has two components. The first one is order P, and the second one is order P squared, where P is the number of parameters. So this says that, well, we should do something, right? This cannot really work when P is very large, which is the case in many applications. So, so what do we do? Okay. So it's not so hard to imagine that if we have the W's, the WK, if the WK is our estimate for the gradient at the parameter theta k, then the derivative of the map that sends theta k to WK Well, it will be the derivative of the gradient. In other words, it will be the Hessian of our function. So what we're going to do is to run a linear regression through those points. So x will be our parameter after k steps, and the y will be the gradient. So we just set up a linear regression with this x, this y. And then, of course, we have the estimator for the parameters of the linear regression, the Bn. And then Hn will be just, well, in the usual regression, here we always put a 1, right? So this matrix, the Bn, is not square anymore. So here we put a bar just to pick the first p rows of our matrix. So now this Hn is a p by p matrix. We take the inverse. So our G will be the estimate of the inverse of the Hessian. And we just symmetrize at the end. We take the symmetric part of this. So this Kn, this is our estimate for the inverse of the Hessian, right? So we use it as our estimator. And we do something a little bit different. We take steps which are not of the form 1 over n, but are instead of the form 1 over n to the gamma, where gamma is 0.6. And finally, we do one averaging of our estimates. And this theta n will be the actual estimate of the parameters. So you can think about it as theta n being at the center of a cloud of points that are moving with speed 1 over n to the gamma. So from theta 1 hat to theta 1 2 hat, we took a step of size 1 over n to the gamma. But then we take the average of those at the center. So this is the actual estimate of the parameters. So this is not that new. I mean, this was studied before, but it wasn't analyzed. Well, it was analyzed by Lai and Robbins, you know, the people who started all this stochastic optimization in '81, the year I was born. So it's been here for a while. But I think back then we didn't have that many parameters or computers to try to use these estimators. So anyway, the name of the algorithm is Affine invariant, and the reason is just that if you change the coordinates in the parameter space, the optimization doesn't change, right? So it behaves well with respect to change of coordinates in the parameter space. So anyway, for any linear transformation, if you optimize f, it's the same as change the coordinates, optimize, and then change coordinates again. So does it work? Well, let's see. There is a simple example, like a toy test, right, which is just a constant curvature function, which is using some paper of Licon. No more pesky learning rates. So it's very simple function. We have constant h. And then, well, this is just the function. So anyway, let's see what happens, see if this works. Oh yeah, also some publicity, right? Everything is on GitHub, so you can just go here and run all the code. Moreover, I don't know if you've used this tool, Travis. This is very good. You just ensure that your code will compile in a Linux box, you know. So you can be sure that this will run. There's no... If you want to use it, just go there. So anyway, this is the result of taking these gradient samples. This is 1 million. And then this is the alpha. Here is the parameter, the alpha optimal. We got this one. Our estimator is nearby. It's not quite there. But then here is G, the inverse of H. And our estimator, I mean, you can see it's like just very close, right? This is not like a very interesting example because it's a toy example, right? I mean, there's constant curvature, but still, at least the estimator is working. We're getting the inverse of the Hessian. So anyway, we go back, view. Okay. Okay, so, I mean, just how do I arrive to this type of problems? I was working in some financial applications where we had some Monte Carlo method and some function that was like the one that I just talked about with some noise. And then over there, it was the case of an American put option, and the parameters will give you the parameters for an execution boundary. But anyway, at the end, this is just a graph of the variance of the estimators as a function of n, where n is the number of samples that we take, and this is the variance of the estimator. So we get the convergence for this type of problems, which is of size 1 over n, as we said before, right? The error is like 1 over n. So anyway, just a nice graph with the result. These are just the results of the optimization in the case of the American option problem. So anyway, this worked very well, but these are just 2, 3 parameters. So how do we do it with more parameters, right? That's the interesting part. So, so first, we can do an online update of all the estimators, right? So this G, which is the estimator for the inverse Hessian, can be computed online just with the previous one. And this Tn plus 1, we have these plus 1s that were calculated here before, and they depend on the estimator for the matrix B and also the estimator for the matrix P. So what is the matrix P? P is just the precision matrix. Our design matrix transpose times X inverse. So anyway, there is an online algorithm to update our estimator, which is very good because we don't have to calculate the inverse of anything at each step. We just do product of matrices, and this way we have an estimate of the inverse. So that's quite something, right? I mean, we don't want to be estimating inverse of large matrices. So, so we have this. So what do we have? Well, there are 2 key features for these formulas. One is that the number of operations, right? Even though we're using square matrices, we don't get p-cube operations. We just get p-square operations. Because all we're doing, like if you look, for example, here, this is vector times matrix, so that's p squared. This is vector times matrix, that's p squared, and then vector, vector. So the most complicated computation you're going to do is matrix vector, which is p squared. Well, there's another key feature, which is this update for G is a rank 1 update, right? This matrix that you have here is just, well, it's all of this has to be a square matrix, right? But this Gn times Un plus 1 is a column vector, and this Vn plus 1 times G, this is a row vector. So it's a square matrix, but it is a rank 1 matrix, right? So just remember that, because we'll use it later. So, so how do we implement this in an interesting case? Well, I found this beautiful library called Torch 7, developed by IDIAP right here. Not anymore? But do you still have some people working on no. But not maintaining the library anymore. Well, anyway, you did a great job. I really like this library. So anyway, first of all, it's open source, which is just nice. You can see all the code. And so you can play with a lot of models very fast. It's written in Lua. So that's kind of like Python. It's just a scripting. So, so you know, OK. There's other people. Well, it was maintained by these labs before. Now there are more labs. And as they say, now they work at Facebook, Twitter, and so on. Anyway, since we're going to be doing a lot of linear algebra, we need support for CUDA and OpenMP. And I didn't get to actually write code in CUDA, but the library uses CUDA, so I can use a video card to do all the multiplications and everything that I need. And it has very recent models, right? Like, for example, Dropout, which was like 2 or 3 years. They was developed like 2 or 3 years ago. So you have all the models that you want already implemented. And, well, of course, the parameter theta is just the weights for the neural network. And the sensitivity analysis is just the back propagation algorithm for the model, right? So we just take the derivative, the gradient of our loss function with respect to the weights. And best of all, many optimization methods are implemented, right? So if you have a new optimization method, you just program it, put it in the library, and then you can run it with yours. So Okay, so what happens here? Well, so here I took a very simple example, which is a convolutional neural networks. The number of parameters is 4,000, so that's quite big to be used in a square matrix. We minimized the usual, the negative log likelihood, and I was lucky enough to get a Tesla K40 from NVIDIA for free. So that's nice. So thanks, NVIDIA. Okay, and this is the limit on the number of parameters that we can use. If we go beyond 4,000 parameters, then we just don't have enough memory to store our square matrix, right? But 4,000 parameters is quite enough if you think about it. But anyway, so here we do just the usual, the first thing that anyone can do, just the MNIST, the digit recognition. And then what I do is just, I run the stochastic, the gradient descent, the stochastic gradient descent for a while. And then at some point, I turn on the stochastic optimization using the inverse of the Hessian. And this is what happens. So here, the X label is just the number of epochs, and the Y label is the precision of our method, right? So here we're recognizing 75% of the images with this model. And then, and then there are two graphs, right? The left graph is the training error, and the right graph is the test error, right, in an independent set. And what happens here is that as we go along, and we turn on the estimator for the inverse of the gradient, like very fast, we are converging, at least in the test set, like very fast. And something similar happens in the, in the train set, and something similar in the test set. Like here we have a huge variance, but as soon as we go into the inverse of the Hessian, we get a smaller variance and close to the maximum that we've seen so far. So, of course, I mean, still the stochastic gradient is faster. Like one iteration here is faster than an iteration here, but not by much. It's maybe a factor of 10. Like this will take me 1 millisecond, and here it will take me 10 milliseconds to do this, right? I'm also using a lot of parallel processing here for all the matrix multiplications that are happening around with the video card. So I mean, it is essential to have a video card to do this. Otherwise, you wouldn't get this comparable result. And then we were like, okay, so we have something that kind of works, but it's not close to the number of parameters that we have in the state-of-the-art neural networks, right? If you look at the state-of-the-art neural networks, I've seen 8 million parameters, right? So what do? I mean, I cannot run this with 8 million parameters. So let's try to do something. And here comes this observation that for this algorithm, the updates are rank 1 updates. If you have an SVD decomposition for a matrix G, so here G will be the inverse of the Hessian. So if you have an SVD decomposition and you add a rank 1 update, then there is a very efficient way to calculate the SVD decomposition of this new matrix, right? Now we will have U hat, U bar, S bar, V bar, and this was done by Matthew Brand. And it's very simple steps. You just calculate these vectors, M, N, P, Q, their norm. This one is just a number, so this inverse, so this is no computational work. The most computational work is when you ensemble all of this in this matrix. So what size is this matrix? This matrix is S, the size of S plus 1. And S was, well, this is an a thin SVD decomposition, right? Because we want to have low memory, right? So this matrix S that is in the middle is an R by R matrix. The matrix U will be an N, well, here we have P parameters, so it will be P times R. So S is R times R, and V will be R times, whatever. So the point is that this matrix here is R by R, where R is the rank that we're going to use in the decomposition. And this matrix U is not P by P anymore, it's P times R. So we will be able to store all of this with few memory. So, okay, so we have the decomposition. And here, this matrix here, then it becomes an R plus 1 times R plus 1. And then here, in this low rank matrix, this is where we do the SVD decomposition. We take this matrix K, and then we do, again, SVD. So we have changed the problem of doing a full SVD in a P by P matrix to doing the SVD just in an R plus 1 times R plus 1 matrix. So we do this, and then we have this algorithm is exact. So if we have the SVD for G, then this gives me the SVD for the updated G. It's just that the rank is increased by 1, as it should be, right? So if I actually do this, then I'm not going to be keeping the memory low anymore, right? Because at each step, I'm going to be adding a rank 1. I will be increasing the size of my matrices by 1 with each new iteration. So what I do is just, okay, I take the exact algorithm, and then I just keep the largest R eigenvectors, right? So if I add rank 1, the rank increases by 1. Okay, so now I have one more. I just keep the R, the biggest R one. So anyway, so this way we keep an algorithm that have an SVD decomposition for the inverse of the Hessian, and now this can run with any number of parameters that I want. So let's run it. So now we do the same. Now we change the data set. Why did I change the data set? Just because I wanted to take some state-of-the-art result. So what I did is just to look a convolutional neural network with dropout and 9 million parameters. And the data set is CIFAR10. So when I did this, the state-of-the-art was like 89% of accuracy, something below the 90%, right? Now I think Google and, I mean, this year, I haven't tried this with the new neural nets that they've done. I don't know if they are now close to 100%. But anyway, when I did this and I picked this neural network, the error in the training was below 90%. So now here I run and this optimization is whatever they have. It's like a stochastic gradient descent, maybe with some normalization at the start, or you know, whatever they do, I do it with them. And then in the epoch 20, then I change to using this SVD decomposition with rank 1. So I just did rank 1. So if you think about it, rank 1 should be as fast as a stochastic gradient, right? If I'm approximating my Hessian with a rank 1 matrix, all I'm doing is multiplying by a vector, right? And that's it. So it should be that's actually order n. So these iterations here are as fast as a stochastic gradient descent because I took rank 1. But anyway, we can see that as we use the new algorithm, we have a small jump. We don't have a big jump anymore, right? Because we are not using the full Hessian. We're just using one eigenvector. But anyway, we keep going, and we go above the result that they have, which was below 90%, so 93, 94%. But all of this is in the trained set, right? And look at what happens on the test set, right? So on the test set, we just completely go out of the, you know, we go even below 10%. For CIFAR10, that's below being random, right? And then just up. So I don't know. I mean, I know that for this type of problems, people usually do like a cross-validation while they are optimizing, right? So they keep maximizing, in this case, the precision on the training set till they start going down on the test set, and then they stop. So that's something you can do here, but I haven't done it yet. I'm just really focused on the training part and the stochastic optimization part. But what should we get from all of this? Okay. So up to the memory limit, it is possible to use the full hashing, right? And moreover, here I want to emphasize, when people work with, they are working to try to do the computations in parallel, right? But if you have an online algorithm, there are not many places where you can usually use the parallelization, right? Because since it's online, you're moving one step and then the next one, right? So you cannot do the online optimization in parallel. All you can do is that the steps become, like you can parallelize the steps. You cannot parallelize the whole thing. So each step in our algorithm, well, here we use the power of the video card because we're doing a lot of matrix multiplication. So this is costly, but it's fully parallelizable. So that's not too bad. So we do reduce the error, and we use the full hashing. Of course, beyond the memory limit, we cannot update the SVD exactly. We have an approximate update for the SVD. But that works at least in the training set. And of course, what I would really like to do now is to analyze the error as we increase the rank of the SVD decomposition, right? Because in principle, I mean, I just did rank 1, but I could probably get up to rank 4,000, right? As I did before, right? In the previous method where the memory only stopped me at 4,000, right? So here, I probably can get up to 4,000 with the rank 1 of with the rank decomposition. But anyway, that's work to be done. And moreover, analyze how the error is decreasing as we increase the rank of the SVD approximation. Right? So that's it. And you can play with all of this. Again, it's on GitHub. More promotion. Just go, click, look at it, try it in your models, see if it helps you. If you ever feel like the stochastic gradient isn't doing it for you, just try this. And I really suggest to use Torch 7 because it's just very fast, very well implemented, and you have many models to compare. Okay, that will be it.